right, so I want to start today just reviewing Snell's Law because we had some issues with that last time. And if you run into questions on Snell's Law on the registry, they'll usually be one of three different types. So I'm going to go over the most common types here. One thing you can remember is PORN. Things that are, this means perpendicular, orthogonal, right angle, or the normal line. So they'll use all of those different terms to describe a line that is perpendicular or orthogonal or at a right angle to an interface, okay? So that's an easy way to remember this normal line to your interface. All right? All of these mean the same thing. They mean an angle of 90 degrees. And if you're curious, this is posted on Blackboard if you want to look at this there. Okay. Yeah. Yeah, this is your interface here, and this is a line that's perpendicular or orthogonal to it. Okay. So if we have three separate media, and that's what I've got here. I've got two interfaces separating three different media. And this one I'm saying is soft tissue is at 1540. This one is at 1460. And this one is at 1320. So they'll give you three media with different speeds. And your task is to find out where on these 5 locations can the sound beam, which is represented here by this red line, end up at. Okay? So we'll put a little arrow here that this is the sound beam coming into the first interface. All right? So this is faster than that, or this media 2 is slower than media 1. So which way will the sound beam deviate when it gets to the interface? Towards the normal, right? Is that right, Anna?
The other way.
Okay, you're saying it'll come out this way. Okay. It's coming in here. It'll deviate towards normal. This is my normal line here. This is my normal line. This is my interface. Okay? So this is my normal line here. So yeah, it's going to come up and it's going to go this way. We don't know exactly how far, but we know it's going to go that direction. We could calculate it if we know what that angle is. But you usually don't have to. It usually will be moving one way or the other. Can it ever get back to A or B? Not really. Yeah, so we can eliminate them. So we're kind of left now with either along the straight line to D or C or E. Okay, now when we get to this interface, this is faster than that, so which way is it going to go? Towards the normal, right. A little more towards normal, so the best answer would be C. Okay? All right. If this one happened to be faster, so we'll say that now it's back to 1540. Okay? Then we know that when it got here, it would deviate out, and then the answer would be either D or E, depending. But that's sort of what you look for, is what is the best possible answer. So if that one again was, we had that originally at 1380, I think. Again, it continues deviating towards the normal. And C becomes the best answer. And these kind of questions, they won't give you something that is too ambiguous. There will be a definite answer. So we have the normal path here on this is shown. If you're looking with the screen over here. And again, this is one where I've given you on the PowerPoint slide, I've given you that media 1 is soft tissue, media 2 is slower, and then media 3 is quite a bit faster. So not like the one I've drawn on the board here. All right, so in this case, we've got the sound entering at a different angle, but it's still going to deviate towards the normal, okay, in the first material. And then we know that when it gets to the second interface, now it's going to deviate away from the normal because that was faster, correct? So when we get to that, it deviates away, and it should be B is your correct answer on these on the PowerPoint. Okay. So you just kind of work through the path and figure out where it goes as best you can. All right. So now here is another type of Snell's Law question that typically shows up on the registry exam. Now we've got 3 different velocities of the media, and this one says the sound beam is entering with an incident angle of 0 or normal or perpendicular or right angle to the media. So where is it going to end up? It won't change direction. No matter how much the speed of the media changes, if it's entering at a 90-degree angle, it will not deviate. It'll stay at 90 degrees. So it'll go straight. Okay? That's another typical Snell's Law question, though this isn't really Snell's Law because there's no angle, so it just goes straight. Okay, then the last type that you typically run into is this, where the media has the same velocity. All 3 media have the same velocity. And in this case, where the angle starts with an incident angle of 50 degrees, it just goes straight. Okay, if the media has all the same velocity, the sound doesn't change direction. Okay. So those are typically the 3 that you see on registry exams. They might have a very simple solve the equation kind of thing. In that case, you do need to know Snell's Law, which is real simple. Who can tell it to me? Stephanie? Can't tell me?
No.
Okay. Brent?
That's what I was trying to figure out.
Okay. C1 over C2 equals sine angle 1 over sine angle 2. Okay? That's Snell's Law. That's it. One of these won't be given to you. You have to do the algebra to solve the others. Okay? If they give it to you, then they'll probably give you numbers that are easy to work with. All right? A very, very common one is to give the known angle as 30 degrees. What's the sine of 30 degrees? Anybody remember? 1/2. Yeah. Yeah. That one is real easy to remember. It's 1/2. All right. So that was Snell's Law in a nutshell.
Do we memorize what all the signs equal in order to figure it out how to calculate it?
You'll need to know the sine and cosine of 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay, we'll need to know those, and I'll show you how to do that. I didn't really have it planned for today, but we'll see how much time we end up with. And if I have time, I'll go through that and show you how to do those angles.
So as long as we know those, then we'll be fine.
Yeah. Sines and cosines of those angles are important. And if we don't get to it right now. We will get to it when we start working with the Doppler. Okay, we will know those, especially the cosine of 60. When we start into Doppler, we have to have that. Now, I want to move on to attenuation today, because attenuation is actually very, very simple compared to what your book is. Okay, the book goes about this the hardest way possible. So I'm going to go through it a little easier. All right. So Chapter 2, attenuation. The units of attenuation are decibels. Because sound is being attenuated, the decibels are always decreasing. The intensity is always decreasing, so the decibels end up being negative. Okay. This indicates a decrease in power, of intensity, amplitude. These are all synonyms, correct? They all mean the same thing, more or less. Power, intensity, amplitude. Not yet. We can get it there. Okay. It is a function of the frequency and the distance. So if you know the frequency and the distance, and you know the attenuation coefficient, which will always be given to you, then you can calculate the attenuation. It is in no way related to propagation speed. Okay. One of the general accepted amounts of attenuation is 0.5 decibel per centimeter per megahertz. Okay. The book has calculated it out to 0.8 decibels. Like I said, this number, this coefficient of attenuation, will always be given to you if you have to work with this. Okay. So let's go through the 3 main types of attenuation that occurs. There we go. All right. Oh, are we not there yet?
Just the last little equation that you had on there.
Oh, okay.
Sorry.
I hate doing it this way, but I'm going to. Okay. Because I did want to record this for you guys, I'm going to do this. Okay. So if we have a total attenuation of 25 decibels that occurs as the sound wave travels from its origin here to here, and we lose 10 decibels in this media here, how much did we lose in this? 15 decibels, exactly. Does everyone see how I got that? Okay. It's simple. 25 minus 10 is 15. All right, so the total loss of decibels over the media is the total loss of decibels. Okay? I mean, this is the kind of questions you'll get on the registry, honestly. This is it. So 15 decibels here and 10 here, that gives us 25 total. All right, so in this case, this is a little different. All right, we start out with a signal. We lose 5 decibels here. We lose 12 decibels here. What is the total decibel loss?
17.
17. All right, so you guys got that. Okay? All right, now we're going to do one other type. Let me get my pen here. And I'll switch back to the PowerPoint because this will make more sense now. So if we have in soft tissue, I'm saying that we lose 0.5 decibels, okay, per centimeter megahertz, okay? I'm just rewriting that equation up there. If we're using, and don't use a calculator on this, you got to get to do this by hand, okay? If we're using a 5 megahertz transducer, okay, and we travel a total depth of 10 centimeters, what is our loss from attenuation?
25
Okay, so 5. Okay, so you take this number times 5 megahertz times 10 centimeters equals. All right, this is how you do it. A half times 5 is 2.5 megahertz cancels. 2.5 times 10 equals 25 centimeters cancels. You're left with 25 decibels. All right.
Negative 25 or just 25?
Well, that's a really good question. Sometimes you will get a question that says, what is the loss in decibels? Okay. If I ask you what is the loss in decibels, it is 25 decibels. If I say what is the change in decibels, then it's negative 25. Okay? All right. The loss indicates the negative. All right? So, and that's kind of a trick question, and unfortunately they're still using it on some of the registry exams. They're trying to get away from that, but it keeps popping up because they haven't got it out of their pool of questions yet. And that'll be the only difference. Whether it's positive or negative depends on the wording of the question, and that's really not the way to ask a question. Okay? Yeah.
How did you get the megahertz to cancel? Did the 0.5
Okay.
decibels?
Right. So 0.5 decibels times 5 megahertz is 2.5, and then the megahertz cancels because this one's in the denominator, and this one's actually in what we would call the numerator. Okay, so anything 1 over 1 cancels out. All right.
So you pick 5 because you're trying to get low.
I picked 5 because it's a nice number we deal with a lot in our scanning.
And then you pick 10 centimeters.
I picked 10 because it multiplies times 2.5 real nicely. It's just a 10 centimeter depth. Okay, so then if we use the same numbers basically, I'm going to give you what is the okay, so let's rephrase the question here. If we have a signal at 5 megahertz, again, and we image tissue at a depth of 10 centimeters, what is the attenuation, the difference in attenuation when the signal returns to the transducer?
That's dependent back and forth. But we need to know this
So-
tissue type.
Soft tissue.
Or which
I'm
is
giving
maybe
you-
soft tissue.
I'm giving you
Or
0.5.
Okay.
Okay.
We need to calculate.
So anytime you're asked to image something or the return trip, you just multiply your depth by 2, okay? So anytime we're doing a return trip, if we're imaging at 10 centimeters, that means we're sending a signal down 10 centimeters and it comes back 10 centimeters. All right? So whenever we're talking about depth, we double our distance. So it becomes real easy. It's 5 times 0.5 is 2.5. The megahertz will cancel, so we're left with 2.5 times 20, which is, we're back to what, 50 dB? Okay. So we have a change of 50 dB in this situation. So we're imaging. You double the depth. All right.
A question. So what
Sure.
is the difference between 0.8 and 0.5? Where does it come from? You were saying it's always
Yeah.
going to be given, but
Different authors, different research, yeah.
okay.
Yeah. If you look up Frank Mealy's numbers, he uses 0.5 for soft tissue. He uses 1 decibel per centimeter megahertz for muscle, and he uses 0.125 for blood. This author uses 0.8 for soft tissue, 0.6 for fat, and he says that soft tissue and blood are exactly the same.
Okay.
I don't know how they're measuring it myself. I just know that that has to be given to you. Okay? That has to be given to you. Because it's attenuation. Attenuation's always given as a decreasing decibels.
So it's always the
Yeah. Now remember, I said, what is the change is 50 decibels. If I say, what is the loss in decibels, now, because I've worded it differently, I've worded it as what is the loss, then I can say 50 decibels loss. Okay? All right. Just be aware of that. Don't get too hung up on it. Yeah.
How are you doing it with the times, the 5 and the 10 to cross out?
Okay. Let me set up the equation the way I always set it up, okay? When I'm doing it, not in my head, I multiply my coefficient of attenuation times my frequency, 5 megahertz, okay, times my depth. And in this case, I gave you a depth of 10 centimeters. Okay, but I said we were imaging, so we multiply that times 2. Okay.
What's that called? The cosine?
This is the coefficient of attenuation. All right. And so these are below the bar, so they cancel with these that are above the bar. So megahertz cancels and centimeters cancels. I'm left with 0.5 decibels times 5 times 10 times 2 equals 50 dB. All right. Okay. So the causes of attenuation are absorption, scattering, and reflection. Didn't bring the beach ball today. Yeah. Soda's getting knocked over.
Oh, really?
Yeah.
Main cause or main cause?
Oh,
Is it main cause of attenuation?
Main. You're right. It should be main. Let's just change that right now. Main cause of attenuation. Okay. So scattering causes attenuation. How does scattering cause attenuation? Hmm? Right. Doesn't come back. It just disappears. It goes off into another direction. And then reflection causes attenuation because some of it does come back, but it's not going forward in that case. All right. So these are the basic causes of attenuation. All right. So in different media, sound will attenuate differently. Okay, in air, you'll have much, much more attenuation than in soft tissue. All right, and that's why we put the gel on people, is because if we didn't put the gel on there, the signal would just be totally lost in that little air gap, and we'd be done. Okay. Bone attenuates much more than soft tissue. It's one reason why you get shadowing behind bone, exactly. Yeah, because it absorbs the sound. It absorbs the sound. Lung, when you hit lung, you really don't get much attenuation in the lung. Most of it is scattered back and is reflected back to you. So you get a very bright interface, but you don't get a lot of attenuation in lung. Unless it's filled with fluid, yes, of course. Yeah. In that case, you have water. Okay, and water has much, much less attenuation than soft tissue. They've done studies on whales. They know that whales can communicate with each other over distances of thousands of miles, over 1,000 miles. The little whales can talk to each other. It's probably slow communication. They don't have a lot to say, but it can occur over a long distance. Okay, because water does not absorb a lot of sound energy. And whales can be very, very loud. Okay. So that was attenuation in a nutshell. So the type of problems you'll run into are either the type where you have a you need to calculate the total amount of attenuation, and they'll usually say, okay, in this media you had 5, this one 10. Okay. Other cases where they give you the total amount and you have to break it out into the different media that it crosses through. It's just basic subtraction, very simple to do. And then the worst case scenario, they might give you one where you're asked to calculate the attenuation given the frequency, given the depth, and given a coefficient of attenuation. So any questions on attenuation? No problems with the homework, I assume? Okay. 8. Yeah, 8. To set up number 8, it's actually pretty easy. They're saying that the returning echo as a fraction of the transmitted intensity. So anytime you have that, you're basically calculating a decibel ratio. So let's look at that. So calculate the returning echo as a fraction of the transmitted intensity. So we'll call this We're dealing with intensities. And so our returning echo will be our final intensity, right? Our initial echo will be our initial intensity. And I gave you last week, I said that 10 times the log of the ratio of intensities is a decibel, okay? So this is going to give you an answer in decibels. And then it's saying that the loss is what, 25 decibels? So it's saying that this equals 10 times up log here equals 25 dB, right? And because we know that this is going to be smaller than that, we have to put in our negative sign there. All right? So first thing you want to do is just divide 10 out of everything, okay, to get rid of the 10. So we can say log of intensity final over initial intensity equals minus 2.5 decibels, okay? We can assume that our initial intensity was 100%, right? So we could put a 1 in there, all right? So I'm going to rewrite this, just putting a 1 in for my initial intensity, 100%. So log final equals minus 2.5 decibels, okay? So I've got an equation here. I've got one unknown. I can solve for that using mathematics. All right? This isn't a math class. All right. So let's take it one more step because a lot of you haven't had math in a long time. If I write log x equals any number, a, okay, that is the same as saying 10 to the a equals x. This is what a logarithm is, okay? This is an a, not a 9. Okay? That's the mathematical definition of a logarithm. I didn't come up with that. This didn't come from your physics books. This came from high school math. Let's go back a few years. So in this case, we're saying that a equals minus 2.5. So log final intensity equals minus 2.5. So that's the same as saying 10 to the minus 2.5 equals final intensity. And if you plug that into a calculator, I think you get an answer of 0032. Okay? All right. Okay, so that's just basically knowing the definition of what a decibel is, being able to come up with that answer.
So you can always assume the initial intensity is 1?
Yeah. You can always assume your initial intensity is 100%, which is 1.
And
Yep.
so the definition of a decibel is the 10 log initial.
Yeah, this is the definition of a decibel, is this right here. Equals dB. Okay.
So what would the question be if it's not negative? What's the loss?
What would the question be if it was not, if this was not negative here? So if I want to, if I increase my power,
It's 360.
if I increase my power fourfold, what will be the change in decibels? Okay, that's the type of question where you would not have a negative decibels. You have to actually increase something in order to get more, to increase the decibels. Remember, decibels are just a ratio. Whatever this is, whether it's power, intensity, something, the decibels are just representing a ratio of that. Okay, bless you. All right. Attenuation is always given as a negative decibel because it's a loss of, it's a decreasing ratio. All right. Let's move on to the next is computer fundamentals. Computers understand things known as bits, bytes, ones and zeros. All right. This is why we need to know about computers. Because in our ultrasound machine we have something called a transducer, which I'm sure most of you are very familiar with by now. This sits in our hand, and it's connected through lots of stuff to a CPU or a computer. So we're actually using a computer anytime we use a ultrasound machine. So that's why we have to know a little bit about computers. That's the theory. Okay? So let's get into something about computers here. All right. So computers can sense voltages, and if it has 5 volts on something, the computer says, we're going to call that a high voltage. If it doesn't have 5 volts, it's going to be a low voltage. So it can have two things. It can have high or low. Well, those can be binary numbers, zeros or ones. Okay? So we're going to call anything with a high voltage, 5 volts, a 1. Anything with a low voltage, a 0. And we're going to learn to count using these binary numbers. So if I have a binary number, and somebody just randomly pick me a number.
27.
Okay, now you get to throw that to the next person who gets to answer a question. All right, so a binary number. Give me one.
27.
No, that's decimal.
0, 0, 1, 1, 1.
Yeah. 1, 0, 0, 1, 1.
Okay. So anytime you're converting from binary to decimal, which is what we like to do because we understand decimal really well, right? Okay. All you have to do is start out with, this is the ones column. This represents either 0 or 1. All right? So 1. Okay. And I showed you earlier today, I said that 1 was also 2 to the 0. Okay? So now this column is going to be the 2's column. All right? Which is 2 to the 1 or 2. This is the 4 column. 2 squared or 4. This one will be 8. This one will be 16. And then we can go on out doubling every column, right? It's real easy to do. So if I want to add in some leading zeros, and of course we can do that, right? Because we don't worry about leading zeros. This would be 32, this would be 64, this would be 128, and this would be 256. Okay? But they're all zeros, so they don't count. Okay? Just like if I write 95, I can write 00095 in decimal, and that's okay. You can put as many leading zeros on something as you want. It doesn't change anything. All right. So I'm just showing you that you can go out as far as you want with this, and all you have to do is start at 1 and double it each time you go out 1. All right? Start at 1 and double it. Now when we want to convert to binary, all we do here, this has a 1, so we add this number to our total. 1. This has a 1, so we add this number to our total. All right? plus 2 equals 3. This has a 0, so we don't add that one. That's easy. This has a 0, we don't add that one. This has a 1, so we add this number to our total. Okay, and then we have zeros on out for infinity, so we add nothing else to our total, so the answer is 19. That's how we convert from binary to decimal. All right? Is everyone good with that? You can do that in your sleep now?
Do binary numbers have to have 4 digits? 'Cause I know
They don't have to. Usually they'll have 4,
Yeah.
4, 8, 16 digits, something like that. They like to do it in blocks of 4.
Yeah, okay.
Yeah. They don't have to, though. Like this one had 5. That's okay. Okay.
I think like at least 4. 'Cause they have a lot.
Yeah, typically 4 is a good number that they like to use. Most computers will use 8, so we'll go right to here. That will be what they call a byte. 8 bits is a byte. And that's your basic binary. So throw the ball to somebody else. Don't hit them in the head. I think it's on you. All right. So we're going to do the opposite now. We're going to go back from give me a decimal number, and we'll convert it into binary. 12, okay? All right. So what we do is we take our 12 here, and I'm going to erase this. And I'm going to erase these 2 to the whatever power because they're just confusing. All you have to do is remember, start at 1 and double it. Everyone can do that? Okay. All right. So we're going to take 12 here, and what's the biggest number out of my sequence here that I can subtract from that without going below 0? 8. So in the 8 column, I'm going to put a 1. Okay? And I'm just going to subtract out 4. Okay? Now what's the biggest number I can subtract out without going below 0? 4. So in the 4 column, I'm going to put another 1. 4. Leaves me with 0. So I fill in everything else with zeros. So to convert 12 to binary, 1100. That's it. Simple. Has everyone got that?
Yep.
Okay. Let's leave that up there for now. All right. All right, so our binary is everything is either ones or zeros. We saw that. A one bit is either the 1 or the 0. 1 byte is 8 bits. Okay, just like I wrote up here. So if we were going to write 12 as a complete byte, we'd use all 8 bits. Okay. And then 2 bytes is a word. And then if you want to program in computers or something, you need to learn about double words and things like that. But we don't need that. We're not going to program these machines. We're just going to use them. So 1 byte is 8 bits. 2 bytes is a word. That's how computers use data. All right. So when this gets posted, this is the same thing I just talked about. This is converting from binary to decimal and back. So I went through everything here, showing you how to do it. We just did that. Everyone said you were good with it, so I'm going to move on here. All right. Let's talk about some different parts of a computer. One of the main parts that we deal with are called input-output devices. So go ahead and toss the ball to somebody, and boom, Jessica, the ball. So what is an input-output device? Give me an example of one on a computer. Or a computer or an ultrasound machine. Yeah. A transducer would be a real good example of an input-output device that we use. Okay. Jessica, what else is out there?
Like flash drive.
A flash drive, sure. That's a storage device. Let's toss the ball to somebody else. All right, so give me another example. Storage device, transducers, or flash drive, yeah. Transducer.
Well, I guess it's tech, but I was thinking the lungs, stuff in there.
No, they're not attached to the computer, are they?
No.
Yeah, we're talking about input-output devices. Things that communicate with the computer about the outside world.
Mouse,
Yeah, you'll get your turn.
I'll say keyboard.
Okay, the keyboard would be a good one. Okay, toss the ball to somebody else.
mouse, joystick.
The mouse, the joystick. Okay. Anything else? So far, we've mostly talked about input devices.
What about the scanner?
A scanner. What do you mean by a scanner?
Like the scanner you put the camera down and scan the computer.
Okay, yeah, you're thinking like a closed coupled device or a capacitor. Yeah. That's the one I was looking for. The screen, the picture. Yeah, that's a definite output device. Yeah.
Instead of touch, when it's touch screen?
Yeah, like
A touch screen would be input and output. Yeah. Yeah, but the display is definitely an output device. Yeah. So those are some examples of output devices, input devices, keyboards. Anything that allows that CPU inside the box to communicate with the rest of the world is going to be an input-output device. Okay, so let's talk a little bit about voltage conversion. When the signal comes back from a mass in the liver, okay, so we're talking about a sound wave comes back, it hits the transducer, and it actually causes the transducer to have a voltage emitted from it to the computer, right? That's how it works. The signal comes back, and it's converted into a voltage. The sound coming back can be really strong, it can be really weak, it can be any one of any kind of size, right? It's what they call a continuum. If we map our wavelength, the power of the wavelength, okay, it could be any spot on here has a different voltage, right? If we're looking at voltage here and time down here. Any point on here has a different voltage. So the computer can't understand things that are continuous like that. It understands two things, right? 1 or 0. Okay? And sometimes we have to put things together and we say that it's a combination of 1s and 0s, but they're all discrete numbers. All right? So if we say that the high voltage here, we're going to say is 256, and the low down here is 0, to the computer it has to be somewhere between 0 and 256, and it can't be 128.5. It has to be 128 or 129. These are called discrete numbers. Okay? So right here we're going to say that this is 128 right along here. Okay? So everything has a discrete number. So if we go up, the computer can do this. Okay? It jumps in little jumps to measure anything. It can't see this smooth wavelength. It just has little jumps that it makes. Okay? discrete numbers from 0 to usually about 256 if we're talking about 1 byte of information. Okay? Now, if instead of 0 to 256 here, I said 0 to 1, I'm talking about my bit depth here. Okay, in this case, the computer would only see things that were either all the way at the top, down here, or up here. So it would see like this. Okay, either 0 or 1. Okay, so if I want to redraw that wave and I want it to look more like a wave, I increase my bit depth. I increase the number of little steps that the computer can see. Okay, so if I have a bit depth of 16, then we can have 16 discrete values. If I have a bit depth of 256, then we can see 256 different values, or however we want to talk about showing things. So we're talking about a bit depth, the resolution that the computer is able to see things at. Okay. Bistable, everything is either on or off. Grayscale, we have many different levels of brightness. Okay. So here's an example of a bistable image. We can still tell what it is, but everything is either black or white. Okay? So now I'm going to do a picture of something that has some bit depth to it. And this is the same picture in grayscale. Well, maybe not the same exact elephant, but you get the idea.
Do you show the image?
It's pretty similar. I don't know. Okay. So let's stop there talking about bit depth on computers. Okay, when we get into the ultrasound machines, bit depth is something called dynamic range. All right, if you want to start thinking about how does this apply to the ultrasound machine. But for today, we're just going to stop right here. Computers have bit depth. It's just how many levels of whatever they can measure. Sure.
Could you get back to the binary slide?
That one? That one? That one? That one?
Yes.
Okay.